called general relativity. And by the way, you're always shown pictures of Einstein when he was like 70 years old and the hair was gray and he was wearing the sweater. He didn't look like that when he was inventing relativity. He looked like this. He had black hair. Someone was dressing him nicely. He was combed even, for that matter. And he looked smarter than everybody else just in the picture. The problem is general relativity isn't right. General relativity is not the final word when it comes to gravity. And how do we know that? We know that because it predicts singularities. General relativity says that there are places in the universe where the equations of general relativity don't apply. And the Big Bang is one of those places. The Big Bang is not the necessary beginning of space and time. It's just the place where general relativity breaks down and we can't say what happened. We have to do better. We have to build a theory better than general relativity. We don't have it yet, but we're working on it. So right now, we should just keep an open mind. Here is one idea. We think that the universe is expanding, it's diluting, it's getting emptier and emptier. So if you ask yourself, what is a natural configuration for the universe to be in? Natural means high entropy. There's more ways to be high entropy than low entropy. The universe is increasing in entropy as it expands, and it's approaching empty space. So the natural configuration for the universe is in fact just to be empty space, nothing there whatsoever. And you might think that you're in Boltzmann's problem then. You can't live in empty space. Why don't we live in empty space? Well, there's nothing there to do the living. But now that we think that there's dark energy, that story is no longer true. The dark energy imparts energy to empty space, and as a consequence of that, even empty space has a non-zero temperature. We currently believe, and this is not a crazy theory, this is the favorite theory among working cosmologists, that in the future, the universe that we see will empty out, leaving us nothing but empty space with a tiny but not zero temperature, and that empty space will last forever. So in fact, you have all the problems of Boltzmann's scenario. There will be fluctuations because of that temperature. You can make a brain in empty space. And you're forced with an even more problematic situation where not only would that scenario not work, that scenario seems to be the real world. The future of our universe, the next 10 to the 120 years, will mostly be empty space with occasional thermal fluctuations. The good news is that these fluctuations might lead to things other than just brains. In fact, they might lead to whole universes. So here's an idea. We're back to being crazy and speculative again. Here's an idea where you have a fluctuation into a baby universe. So here's the outside world. What you would see if you were standing in the outside world is you have this temperature around you, and you would see a couple of the particles around you would conspire to crash together and make a little black hole. But unbeknownst to you, inside that black hole, the fields were arranging themselves just right to make an extremely high energy density and pinch off away from the rest of the universe. This configuration starts in a very, very low entropy state. Why? Because it came out of a bigger system, which was in fact high entropy. It was not all by itself the whole universe. The whole entropy of the universe goes up when you make this baby universe because you still have the background and now you also have the baby. So the whole universe increases in entropy and we live here. Not there when it's formed, but in the aftermath. This universe can expand, cool off, and look like the Big Bang. The nice thing about this scenario is you can play it both directions in time. So here's empty space, empty, quiet, parent universe, time running left and right. And if you go from empty space to the right, you make a baby universe that expands and cools, looks like ours, and there's an arrow of time. There's no arrow of time here because it's empty. There's nothing going on. But we have sibling universes. We have friends who are over here, their own arrows of time. Maybe conditions there are very different, maybe not, we just don't know. And if you start in the middle and go to the left in the other direction of time, you can also create baby universes. They will expand in the opposite direction of time. So the whole shebang is symmetric. It looks the same in the far past and the far future. There could be baby universes very, very similar to ours, way in our past, in which the arrow of time is pointing in the other direction. In this scenario, why does entropy go up? Because it can always go up. You can always increase the entropy of the multiverse by creating new universes. Why is the entropy going up visibly in our local environment? Because we are an offshoot of the multiverse's attempts to make more and more entropy. And that is a situation, that is a process that will never end. It will go on forever and ever and ever. Now, is this true? That's a good question to ask. I don't know yet whether or not this is true. The reason why I like this is because there's no cheating. There's no time in here that I put anywhere into this scenario by hand some low entropy, special, finely tuned state of the universe. This is robust. You start with a high entropy configuration, and it goes higher and higher in both directions of time. But we want to do better than that. It's not good enough that a scientific theory makes sense. It actually needs to be tested against the data. So you should be asking yourselves, how will we ever know whether or not there is a multiverse with these properties? And the answer is, I do not know how we will ever know. So we're young yet. We're working on it. We're trying to understand what these theories are. This theory of the creation of a baby universe is not based on well-established physics. It's extremely speculative. We need to do better. We could get lucky. We could have direct evidence of other universes by bumping into them. This impossible-to-understand plot actually comes from a recent scientific paper where people worked out different bubbles of universe with different conditions smacking into each other. And you would think that that would be sort of an ecological disaster, but in fact, for a large region of interesting possibilities, that one universe smacking into another one can just leave a very faint trace in the relic radiation from the Big Bang. This picture here is actually a snapshot of the universe 380,000 years after the Big Bang. This is the cosmic microwave background radiation. These differences in colors from place to place are fluctuations in temperature. The universe is a little bit hotter one place, a little bit colder somewhere else. So if another bubble universe bounces into ours, it might leave an echo in the microwave background. This is something that is extremely speculative, only recently beginning to be investigated, but it could very well turn into direct evidence for a multiverse. More likely it won't. If I had a 50-50 bet, I would say probably that's not ever going to happen. What is more likely to have happen is that we will construct a theory that does make predictions and that also leads to a multiverse. So the multiverse, remember, is not a theory all by itself. It's the prediction of a certain kind of theory. If you have a theory of quantum gravity, of quantum mechanics and particle physics and space and time that predicts that baby universes are created, you can use that to try to understand what happened before the Big Bang. We don't have that yet, but we're trying to put one together. So we're having things like the Large Hadron Collider at CERN, a particle accelerator that's looking at higher energies than anything we've ever seen before. At the very least, we hope to discover a new particle or two, but we'd really like to learn something that we don't know about space and time. That's the great thing about doing new experiments. You never know what you're going to find. So if they get it working, I'm thinking that in the next 5 years, you're going to be hearing a lot of exciting results from the Large Hadron Collider at CERN. In the meantime, is all this profound or crazy? And again, I honestly do not know. I think it's important. That's why I wrote a book about it, available on Amazon.com. And I want to distinguish what we actually do know between what we don't know. So the first three things here are things we know. We know that entropy is responsible for the arrow of time in terms for metabolism, evolution, all those things. The relationship between the physics concept of entropy and our feeling of time passing in our everyday lives is very, very well established. We know that it's been increasing because it was very low in the early universe. We know enough about the fundamental microscopic laws of physics to know that the explanation for the difference between the past and the future lies in the conditions near the Big Bang. It was very, very low entropy. And finally, we know that we don't know why. We know that we don't have currently any theory of what happened at the Big Bang that is absolutely reliable, that you would ever place a fair bet saying that it's probably true. We're working to understand that. So it could be initial conditions put in by hand. It could be something before the Big Bang. It could be that we're part of a bigger multiverse. This is the excitement of doing science. We're not sure yet. Stay tuned, and probably a year or two we'll have it all figured out. Thank you.